Okay. Let's go to our notes page. Page 7. Did we do number 3 on page 7? No. Okay. All right. So let's do another cone problem. I know the first time through, I just want you guys to be kind of follow along, but hopefully we can kind of put things together a little easier now that we've seen it one time and working it through a second time.
Isn't like these problems just like you realize there's like a cone within another cone?
That's right. Yeah, there's a cone within a cone because the water inside the tank forms the shape of a cone as well. Okay, so here is page 7, number 3. All right, a conical tank, vertex down. So that's a sharp point pointing down, 40 feet across and 40 feet deep. So and water is leaking out of the tank. So the assumption is that there's water in there to begin with, and water is coming out of the tank at a rate of 80 cubic feet per minute. Find the rate of change, the radius of the water when the water is 8 feet deep. Okay, so let's draw a, we know that we're looking at a cross section to see that relationship between, so we can build that relationship between radius and height. The goal is we want to get rid of one of the variables or replace one of the variables in terms of the other, but still maintain something equivalent to this equation. But we can build a relationship between radius and height. So I'm just going to redraw this diagram and just do a 2-dimensional cross section of it with just this portion there. So just that triangular portion right there. So what is the radius of the tank? 20. And the height is 40. But the radius and the height of the water level, those are always what? Changing, right? So we have to hold on to let them be represented by variables. So let's create an equation that will relate the variables here. We can say the radius of the small cone is to the radius of the large cone as the height of the small cone is to the height of the large cone. All right, everybody okay so far?
Why split into a triangle?
We're splitting to a triangle so that we can build a relationship between the radius and the height. If I can get r in terms of h or h in terms of r, I can find a replacement for one variable in terms of the other. So right now we're just trying to find what is that connection between radius and height, because ultimately one of the variables has to go and we want to replace it in terms of the other. Now we don't know which one to solve for yet, but I'm just going to just do one more step here, cross multiply. And then when I'm ready for my last step, I can take it. So I'm just setting up for whichever variable I want to solve for. I can quickly do that with my next step, but I don't know yet which one to solve for. Okay, so let's gather some more information here. First sentence, we already have everything we need. if water is leaking out of the tank at a rate of 80 cubic feet per minute, so what is that 80 referring to? Which variable is that referring to? dV over dt. How do you know it's dV over dt? Cubic feet, that's volume. And then minute, that's time. So the only variable with volume and time in it is dV over dt. Okay, any adjustment we have to make with that 80? What's happening to the volume inside the tank? It's decreasing, right? So any rate that's decreasing, we have to make sure we adjust with a negative. So that negative tells us that the water inside the tank is decreasing at a rate of 80 cubic feet per minute. So negative 80 cubic feet per minute. Okay, find the rate of change of the radius of the water level. What are we looking for? dr over dt, okay? That's our goal for this problem. When the water is 8 feet deep. That's height. Height. Now, is this height of the water level always staying at 8 feet? No, right? The next moment, it could be 7 feet, then it could be 6, then 5, right? It keeps decreasing. So what I want to make sure that we understand is that this is not going to be used until the very end. Okay, we have to establish the relationship with height first, or radius first. So we're not going to use this because right now the problem needs to be expressed as a variable to show that there is a changing value right now. Now, once we find a derivative and everything's set in stone and the time moment is established, then we can find a numeric answer at the end. Okay. Now, let's go back to our volume equation here. Okay, again, which variable are we solving for? We're solving for ultimately dr dt. So obviously there's no dr dt right now, but which variable would have an easier time producing dr dt? Which variable would we like to keep? The r, right? The r will just derivative, will just produce dr dt. So we would like to get rid of the h. So we want to find a replacement for h in terms of r. So which variable should we solve for here? H, right? If I solve for h, I can find a replacement for h in terms of r, and that can replace this piece here. Does everybody see why we're going down this path, or why we're making this decision here? Okay, good. So I'm going to solve for h. H is divide both sides by 20.
Sure.
Yep. 40 divided by 20 is 2. We keep the r up top, so 2r equals h. So here's my substitution. This h will be replaced with what? 2r. So we have everything in terms of r. That's good. So the most common mistake that I see is students involving the h when it's not ready for it. The second most common mistake is taking the derivative too early. Okay, so I see some students either trying to do product rule. There's no need for product rule, especially if we can clean this up even further. The second is some students just jump into power rule and they just do power rule for both of these, but we can't do power rule in this form because these are being multiplied. So what we want to do is we want to clean this up, right? Clean this up so that we get a nice expression so that the derivative of power rule can just be applied once. Okay. Now, how can I clean this up so I can get my coefficients together and my variable together and my r's pushed together? Okay, so that's pi over 3 times 2r cubed. Is there anything I do to make it even cleaner? I don't have to, but I just like to. 2 pi over 3. I like to push all the fractions together, let it sit together, and then the variable have their own space. Some students would put a 3 below the r. It's okay. It's just I don't want us to feel like we got to go through quotient rule or we got to deal with a more complicated problem. It feels clean with a number in front of my variable, right? Okay, any questions here? All right, so now I'm ready to find my derivative. Remember, every variable is going to get impacted by time. So v becomes dv dt. Okay, next. 2 pi over 3, does that go anywhere? Stays, right? It's attached to a variable, so it needs to stay there. And then r cubed becomes
2r squared.
right, 3r squared, right? And then what? Say it again. Yep, cancel the 3's, but we still need what at the end? dr dt. Yep. Okay. Yeah, my next step will be to cancel out the 3's, but any questions here from v to dv dt? This is the only calculus step in the problem.
So
yeah.
Whenever you do that, you like always need to bring it down to DRDT.
Right. So because there's an underlying variable time that we don't see, and it's going to end up impacting every variable that we see here. Yeah, with related rates, there's always going to be a time component for every variable. Everybody good? All right, you said the 3's cancel out, right? Okay, everything is ready for us to plug in, but let's just look to see what we have. Do we have dv dt to plug in? Yes. We are solving for dr dt. So that is the unknown variable, and we do see that show up, so that's good. Do we have the radius of the water level? Not directly, not directly. Now, what's related to the radius? Do we have something that's related to the radius of the water level? We have the what? We have the height of the water level. So is there a relationship between the height and the radius of the water level?
Yes.
Okay, what's that relationship? 2r equals h, right? So it doesn't quite give it to us directly, but we do have a pathway to get to the radius. So I can put 8 in for h and then solve for r. So what's r equal to? 4. Yeah, divide both sides by 2, r equals 4. So now I have everything that I need, right? So let's go ahead and put everything in here. dv dt is -80. All right, so we're almost there. We just have to find a way to get to dr dt. And I want you to keep your answer in exact form. I want you to hold on to that pi. So you can multiply the others to multiply and divide the other numbers, but I want you to hold on to pi, like treat it like as if it was a variable in that sense. Because once it plugs into the calculator, it's going to give you a decimal, and then that will take away the exact value portion. So I can multiply the 2 and 16 together, right? 4 squared is 16. 16 times 2 is 32. Okay, what's next? Yeah, divide by 32 pi. Okay, I want you to make an observation here. Where's the pi located? The denominator. So when everything is said and done, the pi is still going to remain in the denominator. So just keep that in mind. I know, and that's a mistake that I've seen in the past too. Students just feel like that pi is out of place and they want to eventually bring it to the top, but it's going to have to stay there the whole time. Okay, 80 and 32 can reduce. I can take a 16 from both, or I can use your calculator to reduce that for you. -5/2, and then the pi stays below. Okay, what's the unit of measure here? Radius is in terms of feet. Time is minutes, so we just put them over each other, right? Feet per minute. Does it make sense that we're getting a negative dRdt?
It's losing water.
Losing water, right? Water is draining out, volume's decreasing, height is decreasing, radius is decreasing, and that negative helps confirm that.
And would there be a time where you ask for the approximate form too?
You mean of this?
Yeah.
Yeah, so for cone problems, anything with pi, I want you to hold on to the exact value. Because on the AP exam, if it's multiple choice, they typically represent their answer as exact. So
Do you sometimes do this like approximate?
sometimes, but I want us to get used to this process. Because if it's approximate, that's easy. You just plug the calculator, right? But to get from approximate to exact, that's a little bit harder. So I want to make sure we know how to get to the exact. Okay. How do we feel? A little better after going through a second time? Okay.
A little bit.
A little bit. Okay. We'll definitely I'll have a few more of these that we can come back to over the next few days. Let's go to second set of notes that I want to go through with you. This is also a similar triangle problem, but this one is, in a sense, it's easier, but it's also very specific. So go back to page 6. So this is a shadow problem. It's a very specific scenario, but it's shown up on the AP exam. So want to go through 2 scenarios, 2 different types of similar triangle. We did one of them, which was cones. That's the harder one. This one, once you know what the rules are, it's a lot easier to do. Okay, so here's the problem. We have a man who is 6 feet tall. So we have, this is represented by this vertical portion of this inside triangle. He's walking away from the lamppost at a rate of 5 feet per minute. The lamppost is 20 feet tall, so there's a lamppost here. The person casts a shadow on the ground in front of them. So that's the Y right here. So as a person is walking towards the lamppost, that shadow is going to get smaller and smaller. But as he walks further away from the lamppost, that Y is going to grow longer and longer. Okay, so there's a couple of moving parts here, but do we see there is a triangle within a triangle here? So we can build that similar triangle relationship with this. Okay, so what we're going to set up is we're going to draw the triangle always the same way. There's always going to be, the givens are always going to be the height of the person walking and the height of the lamppost. And then I want you to do X here and then the Y here. X represents a portion of the large base and Y represents the length of the small base. X represents the distance the person is away from the lamppost, and as he's walking towards and away from the lamppost, this will be the rate of change of the person walking. Okay, so dx dt is the rate of change of the person walking. Now, Y is the length of the shadow. So as a person is changing his position, that Y is changing, and dy dt is the rate of change of the length of the shadow. Now, as the person is walking, the tip of the shadow is also moving at its own speed. So in relation to the ground, the tip of the shadow is going to be affected by both the person walking and the length of the shadow increasing. So as person is walking away, X is increasing. As person walking away, the length is increasing, and both those rates will add together to tell us the rate of change of the tip of the shadow. So let's start off by building a relationship between the x and y. Okay, so we can say this. We can say the height of the small triangle is to the height of the large triangle, which is what? 6/20, as the base of the small triangle. What's the base of the small triangle? Y. Is to the base of the large triangle.
X plus y.
Yeah, it's x plus y. Does that make sense? Not just x, because x is not the full base of the large triangle. It's not x times y, because that's too much. It's x plus y, since that represents the full base of the triangle, right? If this was 3 and this was 5, then you want to make sure that is represented as 8. Okay. Does that equation make sense? Okay. Some students want to do x over x plus y. It just feels more natural to do in alphabetical order, but we don't want to say x over x plus y, because why do we choose y instead of x from top?
Because y is more associated with vertical.
Another reason, y is the top, not x, and why is it y?
Y is like a shadow.
Yeah, y is the full base of the small triangle, right? It's the small base over the large base. Does that make sense? Why we choose the y, not the x? Okay, let's cross multiply here. We eventually want to find the derivative, but it's easier to find the derivative when we don't have to stare at a fraction. So if I cross multiply here, I get 6 times x plus y is equal to 20y. Let's distribute, combine like terms. Okay. What like terms can I combine here? 6y, subtract from both sides. I get 6x equals
14.
Yeah. Now this is an extremely easy equation, because we're just going to find the derivative of this equation. Okay, it's not as complicated as a cone problem where you got to do proportion and make a substitution and clean everything up. Okay, but we are going to find the derivative with respect to time. So what's the derivative of 6x? 6, but what remains? Dx dt. 14y becomes 14 times dy dt. Right. So we have an easy equation to work with. Now we just have to figure out where things go. Let's go back and read the problem here. Man is 6 feet tall. He's walking away from the lamppost at a rate of 5 feet per minute. What can we assign this value? What variable is that referring to?
Yeah.
Dx over dt. What's happening to x as he's walking away? Increasing. So 5 should be a positive value, right? Okay, so dx dt is a positive 5. Okay, how fast is the shadow growing when the person is 30 feet from the lamppost? 30 is x. How fast is shadow growing? What are we looking for here? dy dt. Okay, look at what we have so far. Look at what equation we have. Do we have enough to solve for dy dt? Yes. So let's plug in, right? So 5 goes in for dx dt. What's next?
1.6 times 5.
Divide by 14. Uh, 30 over 14 reduces to be 15 over 7. So for part A, my dy dt is 15 over 7. What's my unit of measure going to be?
Feet per.
Y is feet, time is minutes, so feet per minute. $30 over 14, I just reduced it to make it 15 over 7. Any questions there?
So A and B, like two separate answers.
Yeah, so for part B, well, how fast is the tip of the shadow moving? So what's the formula for tip of the shadow?
Yes.
Yeah. Do we have both to add together? Yes, 5 plus 15 over 7. So rate of change, tip of the shadow. Yeah, calculator can add those fractions for you, but you can also make it 35 over 7 plus 15 over 7, which is 50 over 7.
Let's use add like 5 to that.
Yep, you just add the two rays together. Okay, it's a lot easier than cone problems, right? The trouble spot that students have is just setting up the equation. I think that's, but once you can get up this equation set up correctly, then everything is just pretty straightforward, right? There's not too much difficulty. Now, there's some extraneous information in the problem. What do we never use here?
The like hypotenuse.
Okay, and we never use the 30, right? That 30 feet from the lamppost, it did not matter because it doesn't matter where he's standing. His rate is always going to be constant. And also the derivative did not produce any x for us to plug in. So the reason why I include that 30 is because this is the way that the problem is set up. They always give you information like this and just have to know. And sometimes with these problems, especially that the distance that the person is standing from the lamppost is not going to matter. It's just, it has no impact.
It's
It's
like
a constant
a
rate.
distractor.
Yeah, in a sense, yeah. But I also want to include it because that's the way that they present the problem on the AP exam too. So I want to make sure you guys are aware.
So you said like the equation that we use for this, like C6 misfortune y is like relatively simple. What's the example like a complex one?
Oh, I was comparing it to cone problems.
Oh, okay.
Your shadow problems will always be like this. Yeah, it's not going to feel any different than this. So I meant that's more complicated than cone problems because cone problems is also similar triangles, but it's a lot heavier in this process. We still do similar triangles with cone problems, right? Radius of the small cone is the radius of the large cone, height over big height, but it's the same idea.
We do have a problem.
Yeah, but let's do a shadow problem. See if we can do one from scratch and make sure that you're really comfortable with it before we move on. So can we try number 2? Number 2 is essentially the same as number 1. It's just a different number, right? So see if you can practice that process of setting up, and then if you can do it, at least we can leave it behind. And I know that you're self-sufficient to be on your own when you're studying for this problem later on. Okay, so try part number 2. See how much you can do to set up. Okay, page 6, number 2.
Shadow being in the same place because it's moving towards that. So,
It's still the same place.
okay.
Yeah, it's just not going to be decreased. The biggest difference with this problem is the fact that he's walking towards the lamppost. So that means dx/dt is going to be what?
Okay.
Negative, right? That distance is decreasing. And as he's walking towards the lamppost, his shadow is also decreasing. So, but that would just come up as you do the calculation. So we're expecting negatives for both dx/dt and for dy/dt. Okay. But you set it the same way. Height of the person over the height of the lamppost equals y over x plus y. Cross multiply and combine like terms. 2y equals x. Find the derivative. Every variable gets impacted by time. 2y becomes 2 dy dt. X becomes 1 dx dt. Replace -5 and for dx dt. Solve for dy dt. I get -5 halves. This one's flipped around here. It's easier to get to b first. So I solve for b, which is dy dt. And then the tip of the shadow, I'm going to just add those together. So -5 plus a -5 halves gives me -7.5. Okay, so if you know how to set up this problem, it should feel like a pretty easy process. Right? It's just remembering the relationship here and remembering how to set it up. I think that's the most challenging part.
Oh, so what's the final variable though? It's dx/dt plus dy dt.
Yeah, we can just say that's the answer. We just say rate of change of the tip of the shadow is dx by dt. This, yeah, we don't have a variable name for the tip of the shadow. It's just these two have together.
What would be the unknown variable in the beginning?
Say again.
What would be the unknown variable at the beginning?
Oh yeah, at the beginning of the problem, the unknown variable was dy dt.
Okay.
Once you solve for dy dt, then everything is given to us. Or I mean, everything is solvable, right? This is the only really we're just trying to find dy dt. Once we have this, we can get to a and b because dx dt is already given to you in the problem.
But usually part B is pretty simple. It's just like from what the answer from A is.
Right. Or I like to always find the length of the shadow changing first, and then the tip of the shadow is just adding them together. Okay. There is one more major shape that we haven't talked about, and that is a cylinder. Okay. So cylinder looks like a cylinder's formula looks like a cone's formula. Okay. So I want you guys to go to number, let's see, okay, page 7, number 4. Okay, a coffee pot in the shape of a cylinder with a radius of 5 inches, as shown in the figure above. Let H be the depth of the water, the coffee in the pot. Volume is changing at a rate of -5 pi root H. And the volume of a cylinder is V equals pi r squared H. Now, do you guys see how similar this looks to the cone formula? The cone formula is this with just what in front? Pi over 3, right? Pi over 3. But even though the formula looks a lot like a cone, we're going to treat it very differently from each other. Okay. So
Some are just like 3 cones, right?
It is, yeah, it is 3 cones, but in terms of our related rates problem, it's going to feel very different. So I want to just draw a cone next to it just to talk about the relationship of the water inside. Okay, so let's say we had two different shapes here, and these are both, let's say these are both coffee pots, okay? And we know that the volume is changing. So let's say water is draining out of both of these, okay? I want to talk about the relationship here between the radius and the height. So as water is dropping, is the height changing here? Yes. As the water is dropping, is the height changing here? Yes. As the water is dropping, is the radius changing here?
Yeah.
Yes. As the water is dropping, is the radius changing here?
No.
No. That's the big thing, okay? So the radius here is a variable, but the radius here is a what?
Constant.
It's a constant. That makes the problem a lot easier. That means that radius is never changing. If we know what the radius is, we can replace it and get rid of it without having to hold on to it and do similar triangles. So the struggle that students have with this, even though this is an easier problem, is they want to force a similar triangle into the shape when there is no need for similar triangles. You guys see that there's no triangle here. And also there's no need to build a relationship because the radius is just a number, and that number can replace the variable at the beginning of the problem. There's no need to hold on to it. Okay. Now, what is the radius of this coffee pot? 5. So at the beginning of the problem, we can just get rid of the R and the problem will become a lot easier. So I want us to make sure that whenever we see a cylinder problem, that in our minds we're thinking, okay, this is an easier problem than cone, and we don't have to go through similar triangles. So V equals what? Pi times
5.
Yep, 5 squared times H. Let's clean this up. V is equal to 25 pi H. Right, so now you see we're already ready for the derivative. With the cone problem, we got to go through all these steps to get to that place. But when I see students work these problems, they force it into a similar triangle problem, and then it just goes down the wrong step. Okay. And the reason why is because I think it looks so much like a cone formula that we want to treat it like a cone problem. Okay, let's find the derivative, and that way we can have everything in front of us. Okay, so V becomes dV over dt. 25 pi H becomes good. Yeah, so 25 pi is not going anywhere. It's still attached to the variable. When the H goes away to a 1, the dH dt shows up. Okay, so we have the calculus step taken care of. Now let's go back to the problem. Let's see if we can gather some information from the problem here. It says the volume of the pot is changing at a rate of -5 pi root H cubic inches per second. Okay. What can we assign this to? dV over dt. It already tells us negative, so we don't have to adjust the signs, right? It's already
dV dt.
Yeah, dV dt. Mm-hmm. What gives it away? How do we know?
Oh, the cubic.
Yeah, cubic. Also, they tell us the volume, but even if they didn't tell us the volume, yeah, the units of measure is always going to be the one I think is most helpful. That's consistent. I always have to give that to you.
All for the second cubic. The second time.
Yeah, the second time. And also find dH dt as a function of H. So that just means that when we find our answer, H is going to be in our answer. Okay. Do we have dV dt to plug in? Okay. And we're solving for dH dt, so should just be should be pretty quick, right, to get to our answer. So replace dv dt with negative 5 pi root h. (25 pi). Then dh dt. I want to solve for dh dt, so I can do what? Yeah.
You have to put the h into h of 1.
No, because we don't have to find the derivative of this. We just have to kind of leave our answer, but it's not wrong if you put it to the 1/2. Okay, but I don't have to because I'm not having to do a derivative of this. Okay, what can I do to reduce this? Yeah, the pi cancels out, negative 1/5. The root h stays up here. Okay, what's my unit of measure here? Yeah, h is feet. Oh, sorry, inches. H is inches. T is seconds, so inches per second.
You don't have pi in the integer.
Oh, in this case, why do we not have pi in the answer?
We use a cancel
They
that.
canceled out. You guys have homework tonight. Oh, by the way, some of the homework problems, especially yesterday, had theta in it. So anything that, if you see any more homework problems that I accidentally assigned to you with theta, we're doing radians and trig related rates later in the semester. So if I accidentally give these to you in the future, just skip them. Okay, we're not going to do anything theta related with related rates or radian or angle related until December. Okay, come get your phones.
It's a lot worse.
Okay, good. Thank you.
It's a lot worse. Just think about like drawing the lines for like that. Oh, yeah, that's terrifying.
So like number 9.
Let me see.
My drawings are so bad. My drawings are like that.
I mean, it's fun, but like,
Yeah, 19. Yeah, skip 19. Yeah.
And like 54, that it's like QE cosine.
Yeah. Skip that too.
Just do the other 3.
Yep. Mhm.
So what it's like here, so they rotate, but it looks like it's like a base. They try to rotate your model. You give them.
Yeah, we can just circle that or remind me to look
Okay.
at it.
All right, and then do you want to white this out?
Yeah, just like that. Appreciate it.
I mean, he would know that every time he passed him, there would be more calculated.
Yeah.
I don't know if that's, I love being called.
So we could try to
Do it a circle there.
Yeah, just circle that and so I can look at it and decide.
Good.